Now, welcome back. So let's finish the last bit of problem 2 on numerical integration by Simpson's third rule. So remember the problem that you're solving, problem 2. This is the problem. Find the exact value of this integral and then use Simpson's third rule to approximate the above integral by taking this number of intervals. So we have shown for 4, 6, 8, and 10. So now we want to show how this integral or the value of this integral when you take n 12 sub-intervals. So n equals to 12 implies h is 1 minus 1 over 12, 2 over 12, which is 1 over 6. And remember the function is 1 over 1 plus x squared. So you make a table of values, x and f. So negative 1, add 1.1 over 6, you get negative 5 over 6. And then next will be minus 2 over 3. Adding 1 over 6 will be negative a half. Next, negative a third. Next, negative 1 over 6. Next, 0. Next, 1 over 6. Next, a third. Next, a half. Next, 2 over 3. Next, 5 over 6. Next, 1. So when you put these values of x in this function, you get this a half, 6 over 61. So this 9 over 10, 4 over 5, 9 over 13, that's 6 over 61, and this a half. And then once you have this table, you label this as F0, F1, F2, F3, F4, F5. Next will be F6, F7, F12. Now you write the formula by Simpson's third rule. We have h over 3 into x plus 4o plus 2e. So our end ordinates will be F0 and F12. So we'll have I h over 3 F0 plus F12 plus 4 into F1 plus F3 plus F5 plus F7 plus F9 plus F11, and then 2 into F2, F4, F6, F8, F10. You don't include F12 because it was one of the endpoints, so that's the endpoint. So I remember h in this case is 1 over 6, so dividing by 3 is 1 over 18 into a half plus a half plus 4 into 6 over 61 plus 4 over 5 plus 6 over 7 plus 6 over 7 plus 4 over 5 plus 6 over 61 plus twice 9 over 13, 9 over 10, 1, 9 over 10, 9/13. When you work out this one, you get 1/18 into 1 plus 18.90509526 plus 544/65. I will be 1/18 times 28.27432,603. Carrying out that operation, you get I to be 1.570795891. So error, call it E5, is exact, is a half pi minus this value this will give us 4.362829 times 10 decimal minus 7. And percentage error will be given by the same error over the true value times 100%. When you work out that one, you get 2.777458.048 times 10 to the power minus 5%. Now, when you compare this value, the error when n is 12 is less than when n is 10, and error when n is 10 is less than when n is 8, and error when n is 8 is less than error when n is 6, and also error when n is 6 is less than when error is when n is 4. So the trend is that in general, the higher the number of subintervals, the better the approximation. Or simply the less the error, and vice versa. So that's usually the same trend like we saw in trapezoidal rule, that the number of, when you increase the number of subintervals, then you get a better approximation. And then same number of subintervals, Simpson's third rule yields accurate result as compared to trapezoidal rule. You can always confirm for the calculations we did for trapezoidal rule and what you've done for all this example on Simpson's third rule. So that's the solution. Thank you.